So hey guys, welcome back to the channel. This is your physics buddy and I came up with another session on electricity and magnetism unit. This is going to be the fourth session, and in this session we're going to talk about electric field and intensity of electric field in detail. We'll start with some problems on superposition principle. We'll understand how electric field line is drawn from different charge configurations, as well as we'll talk about how electric field can be calculated. If you are new to the channel, just make sure you subscribe to it and do check out the previous lectures uploaded on the channel already. Let's start.
Once again, because this is the same one we did in the last class also, using using Q only. Then we'll move towards the electric field. So basically there are three charges located at the corners of an equilateral triangle, and as you know it is an equilateral triangle, so it is going to be equal distance. Now what you have to understand here is the question says what are the direction and magnitude of the force on Q1. So this is my Q1. So now let us try to understand the direction of force acting on Q1 due to all other charges. So Q2 is positive, Q1 is positive. So the force which acts between these two charges is going to be repulsive in nature. So Q1 will experience force in this direction, in the opposite direction you can say. So that opposite direction can easily be represented using this line. Again, the line of force should matter. So force will act in this particular direction. Similarly, Q3 is negative and Q1 is positive. The force which will act between them is going to be attractive. So the force will act in this direction like that. Now this is something you have to understand. One is in this direction, another is in this direction. And what should be the angle between these two forces? That is what we have to think. Now just think about it. This is 60 degree, so this is also going to be 60 degree. This is 60 degree, this is also going to be 60 degree. So angle between these two forces is going to be 120 degrees. Now this is something I can assume that force on 1 due to 2. This is something I can assume as force on 1 due to 3. Now let us try to find out the value of force on 1 due to 2 and force on 1 due to 3. So the value of force can be written as k q1 q2 by r square. So I'll write it directly, k q1 q2 by r square. So as you can see that the magnitude of these two forces are definitely going to be same. Why they are going to be same? Because q1 is always positive 4, q2 is positive 4, whereas q3 is negative 4. So negative sign is only responsible for giving us the directions, which we have already mentioned in the diagram. So the magnitude will remain same. So in both the cases, force will going to be same. So I can just mark it as F. Now we have to find out net force. A net force can be found using the relation of resultant that we learned through parallelogram law. So we'll simply write it is going to be F1 square, F2 square plus 2, F1, F2 cos 120. Why? Because the angle between these two forces are 120 degrees. Now this is the most important part about solving these questions. You have to actually understand what angle these forces are making with each other, because then only you can find out the resultant force. So first of all, we'll find magnitude, then we'll talk about the direction as well, because here the direction is important. So this is going to be, now what is the value of cos 120? Tell me.
Negative 0.57.
Or you can also say as negative half. So this will give us 2f square minus f square. So f net is again going to be f only. That is k q1 q2 by r square. Now let us substitute the values of each and every number here. K is supposed to be 9 times 10 to the power 9. Q1 is supposed to be 4 microcoulombs. So microcoulombs I already told you. 10 to the power minus 6 into Q2 is again the same. 10 to the power minus 6. What is the distance between each force? 20 centimeters. The 20 centimeters in meters can be written as 0.2 whole square. So I'm just writing it as 0.2 times 0.2 because we have to do the square of this. Once we solve this, we'll have the answer. So it is going to be, let's solve this. So this will cancel out. So 9 into 4 is 36. 10 to the power 11, 10 to the power minus 12. That is going to be 3.6 newtons. That's it. 3.6 newtons. This is going to be the net force acting on force charge. Now, if we talk about its direction, force will going to act in this direction. And this is something which can be represented using I cap. That's it. This is how you are supposed to answer the question. Or we can also say that the net force will act in horizontal direction parallel to base of the triangle. But again, just make sure that whenever you are solving such questions, you will be writing directions also, because the question says find out direction as well. So this is the question which we did in the last class also, and you have to understand how we're supposed to solve this question.
Okay.
Now, again, another question. The same question is there. You have to find out the direction and magnitude of force acting on charge Q2 and on charge Q4. So whenever you're doing such questions, make sure you just figure it out that which is positive, which is negative, or force is attractive, or force is repulsive. Let me just do the first part, and second part you can easily do it. So Q2 is there. So this Q2 will be experiencing force due to this all three charges. So let us talk about Q1. So Q1 and Q2 both are negative in nature. That is same nature of charges there. So they are going to experience force that is repulsive. So Q2 will experience force due to Q1 in this direction. Similarly, Q4 is applying force. Basically, Q4 is positive, Q2 is negative. So they are going to apply force in the force which is acting between them is going to be attractive. So along this line, there is an attractive force which might be acting in this direction. Now Q3 and Q2. So Q3 is positive, Q2 is again negative. So this is again going to be attractive force like that. Now we'll try to find out the each and every force, also the resultant, because they're not going to be same here. So this is something force on 2 due to 4. This is something force on 2 due to 3. Now this is not an easy one. It has a lot of calculations here, because the angle between each and every force is quite tricky. So this is F21, this is F23, this is F24. So let us try to find out the value of each and every force. So F21, what you can write about it? It is going to be 9 into 10 to the power 9. Q1 and Q2, they both are 10 microcoulombs. So let me just write it as 10 into 10 to the power minus 6 whole square, because nature of value of both the charges are same over distance between them. Distance between them is 0.1. So 0.1 square. If you solve it, you get the value of F21. Similarly, if I find F23, it is going to be 9 into 10 to the power 9. Q1 is going to be 10 microcoulombs, so I can write it as 10 to the power minus 5. If you solve this, you'll get 10 to the power minus 5. Similarly, 5 microcoulombs, so it can be written as 5 into 10 to the power minus 6. Over distance between them is 0.1 only. So you can solve it and you can get the value of F23 as well. Now, F24, this is important, this is interesting. And in order to write this, only the distance between them will change. Like this diagonal is going to be what? It is going to be root 2 times the value of this. So I can write 0.1 root 2. This is going to be the distance between these two forces, these two charges. So here, when you solve this, you'll write 9 into 10 to the power 9 times 10 to the power minus 5 times 5 into 10 to the power minus 6 over 0.1 root 2 whole square. Now, we have to find the value of each. Let's solve this out. So 9 times 10 to the power 9, so it is going to be 10 to the power minus 12, 10 to the power 2, 10 to the power 10. So 9 into 10 to the power 9 into 10 to the power minus 10. 0.1 square, it is again going to be 100 in the top. So here you will get it around 90 newtons. If you solve this, it is going to be 45 into 10 to the power minus 11, and it will come up, cancel out, we'll get 45 newtons only. Again, you need to be good with calculations also, because calculations will play a major role here. And if you can see here, this particular force is going to be the half of this 45, that is 22.5 newtons. So ultimately we got the forces that are going to be act. Now, in order to solve this particular problem, let us suppose few things. What I can suppose this is F, this is going to be F by 2, and this is going to be F by 4. Why I'm taking it this way? So that while I'm calculating resultant, it becomes a little easy. Let me show you how. Whenever you are solving resultant of any two forces, what you need to have the angle between them. Or there is another way by actually solving the component. Now just look at the diagram, this one only. This force F24, this force will have two components, one component along this direction and one component along this direction. Do you know how to find out the component?
It's sine and cos, right?
Yeah. So F24 is going to be here, we can write F24 sine 45, and here it is going to be F24 sine cos 45. So F24 is supposed to be this 22.5. Let us take it as F by 4 only. So it is going to be f by 4 sine 45, which is going to be f by 4 root 2. So here the force which is acting is f by 4 root 2. Here it is going to be acting f by, again same 4 root 2, because cos 45 is also 1 by root 2. Now f23 is what? f23 is f by 2, and this is going to be f. So if you solve these two forces, the net force will be in this direction only. How can you find it? By simply subtracting these two forces. F minus f by 4 root 2, which is going to be the force which will act in this particular positive x-axis. And in positive y-axis, the net force is going to be f by 2 plus f by 4 root 2. Like that. This is what you have to understand. Now, when you take out the resultant, the net force will act in this particular direction. And whatever this net force is going to be, you will be finding by solving these two forces, like this one and this one. So, okay, a little tricky question because you have to solve a lot here. Calculation is very important. So I just want that you to do that part, and without trying these things, you won't be able to feel confident about these questions. That is what you have to make sure that you just
Okay.
solve and try each and every question. Just give time. This particular subject needs time. You have to devote much more time than any other subject.
Okay.
Make sure that you at least try 2-3 questions every day. So this is again another question. We should have discussed it, but it's better that we move ahead. So the next topic we have to discuss is what is electric field. So before actually going to the topic, there is a one such question that should we have asked ourselves before as well, that why this lightning has hit this particular building only, why this building only. So after talking about this electric field concept, we'll be able to answer this particular question, that why this thing happened. Although let's move to the topic. So electric field, what is electric field? So electric field is basically a region which is surrounded by a charge where we can experience the electrical effect, and that is something we call electric field due to a given charge. So I already told you, whenever there is some charge, the charge is actually spreading field around its surrounding, and that field, because of its positive nature and negative nature, will change. So it will depend upon the nature of the charge, which is sometimes positive and sometimes negative, depending upon the charge. So always remember, whenever we're talking about electric field, we're talking about the effect of charge in its surrounding, and that effect is something we call electrical effect, which can be experienced by any other charge which is placed in that surrounding. So that is what you need to understand. Electric field intensity. Electric field intensity is something, or we can say how we can actually define what is electric field intensity. So electric field intensity is defined as force experienced by unit positive charge in surrounding. So whatever force a unit positive charge will experience, that is something we call electric field. So electric field is a vector quantity, is represented by E vector. It is equals to force per unit charge, like that. So if you try to solve this relation, you know, force is nothing but kq1 q2 by r square. Now what happens here is, per unit charge means you'll be dividing any of the charge with given relation.
Yes.
Electric field due to a point charge is represented by kq by r square. Now this is the most important part. Force involve two charges, whereas electric field involve only one charge. So this is something which we will be comparing sooner or later. So we need to understand that how electric field and force varies. So this force per unit charge exerted on a positive test charge at rest at that point. And there is also one thing, limit q tends to 0. So limit q tends to 0 simply representing that force is supposed to become 0, then whatever force any other charge is applying, that is something which we can represent as electric field. That is force per unit charge. Now let us try to understand that how electric field lines look like. These are basically imaginary curves tangent to which will give us the direction of electric field. Like for example, suppose there is some field which is represented in the first case by this particular diagram. So what we need to understand here is that this is not something which we actually see, like they are going, that field is coming out from this Q or Q2 and going into Q1, like that. These are the imaginary lines. We have imagined that this is how the field might look like. But in order to understand that how it actually looks like or how the field is going to takes place, we just simply calculate the tangent. Tangent means we try to calculate the direction of field by actually calculating or by actually drawing the tangent. Like for example, suppose the field is going this way. So at any point you have to find out the direction, you draw the tangent. And that tangent will ultimately give us the value, or you can say that tangent will ultimately help us to understand what is the direction of field. So again, remember, electric field lines are imaginary curves. They are curves heading from some positive charge and going towards some negative charge always. So whatever from whichever point they are emerging out, that point is supposed to be of positive charge. And whatever point they are terminating in, that point is supposed to be negative charge. Although it will be clear soon. So how you can actually draw the field due to different charges. So positive charge is always exert fields outward. That is away from charge. Whereas negative charge, field direction is always towards the charge. So you can see how it looks like. Positive will apply, or you can say will exert field in the opposite direction and outside direction. Whereas negative charge, this is the point where the field will terminate, it will end. So if it will end, it will look like that. Also, another important property, two electric field lines cannot intersect each other. So if this is one electric field line, this is another electric field line, we cannot have two electric field lines intersecting each other. So one field is like that, so another field will automatically go around it. It will not intersect the other field. Why? Because at any point of intersection, if the field will intersect, what will happen? The field will have two directions, and a vector quantity at the same point having two directions is not possible. So this is what makes it a little different from others. No two electric field line will ever intersect each other. Just remember this point. Similarly, the next part here is electrostatic field lines are perpendicular to conductor and no electrostatic field line inside the conductor. Like for example, suppose you have placed a conductor in electrostatic field. Let me just try to explain you through each and every diagram. Suppose there was electric field initially like that. It was uniform like that. So whatever source must be there, we don't care about it. We just observe the field. Now what happens here is I just bring a conductor and place it inside it. So what will happen to the conductor? Conductor is initially electrically neutral. So I assume it is electrically neutral initially. So what happens to this conductor is this conductor will get induced charge due to this field in which it is placed, and that induced charge will be aligned in such a way that positive will be attracted by negative charge and negative will be attracted by positive charge. Always, as I told you, electric field line always start from positive charge and terminate at negative charge. So this is positive Q. If this is positive Q, electric field will be going like that, this way. So I can assume that this particular portion must be of positive charge. This portion must be of negative charge. So what happens here is with the electric field, this electric field which is supposed to be passing through the conductor, that electric field will not pass through like that. What happens here is it just terminate into it like that. Why it is happening like that? Because of the nature of conductor. And this happens due to the property of this conductor that it can have induced charge on its surface. So this is positive. So this particular side of the conductor will have will induce negative charge, whereas this particular side of the conductor will have or induce positive charge on its surface. So this is what it exactly looks like, and this is the reason why this has positive there and this has negative there. Did you understand this particular part of how this charge is induced? Did you understand it?
Yes, sir.
Yeah. So electrostatic field lines are perpendicular to conductor and no electric field line inside the conductor. This is the most important part about conductors. As I told you this thing in the last class also, that if this is a conductor, so we will never draw field line into it like that. There is no field line exists inside the conductor because we already studied the charge only lies on the surface. So if charge only lies on the surface, field will only lie outside the surface or outside the conductor. These are perpendicular to the conductor always. Perpendicular to the conductor means suppose this is my conductor, which I drawn here. So whatever field line is entering or exiting, that field line is supposed to be perpendicular to the surface like that. That is the reason we draw that field not like that, because it is not making it 90 degree or making it perpendicular. Instead of it, the field automatically turns itself so that it becomes perpendicular to it like that. So this is the reason why field line actually moves like that. Understood? So continuous curves in charge, G area. So whatever charge we have, they will form a continuous curve. Electrostatic field line. Now this is very important definition here. Electrostatic field lines is conservative, can define potential energy. Work done in loop is zero. Work done do not depend upon path. I will discuss all these points if it is necessary. Like what exactly your class teacher has discussed in the class apart from this PDF, PPTF shared?
It's mainly this. This is the lecture he gave us. So these are like the slides.
Okay. But still, apart from this, there are a lot of things in this we have to discuss. And this is what we're discussing. All right, let's move ahead. So this is what means, you can see another point. Crowded means electric field is higher. Like for example, I'll assume I'll choose two regions. One is this, another is this, right? So this is the first region. This is my second region. So here you can see that number of field lines in region 1 is way more than number of field lines in region 2. What does it indicate? It also indicates the strength of field in those two regions. So we can say field at 1 must be greater than field at second region. So this is the most important part you have to understand about electric field. As the field lines getting crowded at a particular region, at a particular spot, so it means that the field strength at that point is huge. Let's move. So electric field lines in some of the cases, let us see those cases. The first is two positive charges. So as we know that the two positive charges are always repel each other, so their field line will also repel each other. Positive charge are supposed to, you can say, divert or you can say repel from each other. So the field lines will also do the same by representing field lines like that. Now you can see here that this positive charge will actually exert field from it. So I already told you if there is a positive charge, this positive charge will exert field lines like that away from each other. But if there is another charge which is kept around its surface or around this positive charge, so this field line has to like move, deviate. And this is instead of going like that, they just moved upward so that no electric field lines intersect each other. Similarly, if there is two positive charges, like two opposite charges, positive and negative, so the field from positive charge will terminate into the negative one. And this is something we have to understand here. This shows longitudinal contraction. Whereas in the first case, where the two charges are supposed to be of same nature, this shows lateral pressure. So the positive charge in the second case will actually exert field, and that field will terminate in negative charge, the same negative charge which is kept around it. So whatever positive or negative charge is there, if there are two positive and negative charges, field will come out from positive charge and will terminate into negative charge. That we what have to understand here. Is it clear?
Hello, sir. Is my voice audible?
Yeah. Is it clear?
Yeah. My mom was calling. Sorry.
Okay. So electric field line has tension that tries to get its end together in case of opposite charges. Now, this is a conductor. This is a conductor, you can say a wire or something like that. So in this case, suppose if there's a wire which is having positive charge in it, so field line is supposed to be exerting like that. Similarly, this is a plane, or you can say this is, you can assume it as a sheet. So if this is a positively charged sheet, so field lines will be coming out of it like that. I try to answer this question. You can answer this question now. What are the sign of charges in this particular case? Think wisely.
Both are
And
positive.
try to look at the arrows also. Charges have field terminating into it. So if field is terminating into a charge, what charge it should be?
Uh,
A positive charge exerts field outward,
Yeah.
whereas negative
So both
charge,
should. Oh, okay. No, both should be negative.
yeah, this is what you have to understand here. Now, think about it. Point A and point B. What is the distance between relation between electric field? I mentioned a point in previous slides, and that point will help you to answer this particular question. Think and tell me. See, I told you if the number of electric field lines are crowded in a particular region, the strength is more at that point. So, at which point you can see that the number of electric field lines are little more than the other one. Tell me. At point A, just consider an area, and through that area, figure it out that how many number of electric field lines passing through it. At point A, number of electric field lines passing are 4. Whereas at point B, for the same area, number of electric field lines passing are 2. So if the number of field lines is more at point A, we can directly say that electric field is more at point A. That's it. Just look at the diagram and answer the questions. You don't have to think much. Are you getting it? And from whichever area, number of field lines are passing more, field lines are supposed to be more at that area. That's it. Now, this is the most, you can say, valuable question. If you're able to answer this question, this means you have understood about the field line and its configurations. So the figure shows electric field line configuration due to a charge. So from this, what we can conclude? Now just think and tell me. First of all, tell me the nature of the charge, both of these charges. What is the nature of both of these charges? Tell me. Field lines is going out of it. So if it is going out of it, what you can say about the field charge? What you can say about the charge? Charge is actually emitting field lines, or field lines is going away from a charge. What does it mean? What is the nature of charge? Think and tell me what you understand from this particular diagram. What is the nature of charge Q1 and Q2?
Charge is positive. Q of Q1 and Q2 is
Yeah,
positive from right side and negative from, I think, left side.
mm, both of them are emitting field. Like field is going away from both the charges. So if it is going away from the both the charges, the Q1 is also positive and Q2 is also positive because it is also emitting field. So it is also positive. So both are positive, that is clear. So option 1 and 2, from one of these two options, one is going to be correct. Now, think properly. I just told you in the last question only, number of field lines will decide the magnitude of charge also. Just think and tell me which option should be correct.
It should be, I think, B.
Yeah, it should be P only because Q1 has more field lines coming out of it, where Q2 has less number of field lines coming out of it. So if it has more field lines coming out of it, it means Q1 must be greater than Q2. And that is the reason why option B is correct. So that is how you can actually understand it. Let's move ahead. Now, another question. We have already discussed this particular part as well. Think about it and tell me which option should be the correct one. Read the question once, think wisely, and tell me. We have just discussed this. Think and tell me.
It should be A.
Mm, no.
C.
Yeah, it is going to be C. Just look at this diagram. You already understood this. Field lines try to bend when it is passing through a conductor. So if it is bending at the conductor's point, so C is going to be the correct answer. So for point charge, field lines is nothing but force on Q1 due to that charge, and it is always equals to KQ by R square. Remember the relation, and also it is a vector quantity. So whenever we are solving net field at any particular charge due to other charges present around it, so we have to use vector principles, that is parallelogram law, to find out the resultant. Now this is important. What is the relation, or you can say what is the graph of E and R? So we know E is somewhat inversely proportional to R square. So if it is inversely proportional to R square, as distance increases, field will decrease. I'm assuming this is my origin. So if there's a test charge placed at this particular point, the force will be in right direction, and that force can be represented by positive thing, positive charge. So field and R will keep on decreasing like that. So the graph will look like that in this particular case. Whereas if it is negative charge, the same thing will be for there, but for negative, it is going to be this way, like that. It is again going to be decreased as the distance increases. So as the distance increases, field line will be decreasing, electric field will be decreasing because E is inversely proportional to R square. So this is an important graph, and this graph will be definitely there in some of the cases. So maybe you'll see some problem in tomorrow's test through this particular problem, through this particular graph also. But how we got this graph? Using the relation of electric field only. Now this is the trickiest question. Again, here we'll be using the same part. Let me try to help you with this particular question. So question says that there are 5 charges, each of magnitude plus q, and they are placed at the corner of a regular hexagon. The regular hexagon means all sides should be of A. Find the magnitude of electric field at centroid O. What is our magnitude of electric field? Now let us try to understand. Because of this positive charge, field line should be at point A is supposed to be like that. Because of C, so it is EC. Because of F, electric field is supposed to be at this point. We can write as EF. Because of A, electric field line is supposed to be at this direction. Because of E point, it is supposed to be at this direction. We can write it as E, electric field due to E point. And because of B point, electric field is supposed to be at this particular direction. Now if you just look at these 4 field lines, this is always equals to this particular charge. So the field line is also going to be equal. So what will happen here is E due to E point and electric field due to B point will cancel out each other. And same goes with electric field due to C point will be cancelling out electric field due to F point again. So the net electric field which we are observing, it is due to A only, and that is supposed to be in this direction. And we know it is going to be kq by r square. Now what is this r square? What is this distance? This is something we have to find because r is the distance between the charge and the point. So if you just try to understand, you can write it as kq by r square. And this r, how can you find this r? What is this r in this particular case? For a regular hexagon, this distance from the centroid to the point is also a. So you can write it as kq by a square. That's it. This is going to be your answer. Now, in order to answer these questions, you have to think wisely. You have to think from the forces point of view. If you are able to understand that how forces are actually acting, how field is actually acting, and also in these kind of cases, what you will observe that most of the field lines emitting because of one charge will be cancelled out because of other charge. In case of what? In case of regular polygons, whether it is rectangle, whether it is square, whether it is equilateral triangle, whether it is regular hexagon, whether it is regular pentagon, and all the charges are there. Like suppose at this particular point, D point, there is no charge. If D point also has this positive charge placed at this point, so in that case, net electric field at centroid is going to be 0 because all the field will be cancelled out due to the other one. And this is what this particular problem shows. So is it clear? Is it clear, Arnav?
Yes, sir.
All right, so that's all for the class. Basically, there are a few things that we have to discuss. Is basically one is dipole. We have to find out electric field due to dipole at various configuration, that is axial and equatorial. And some of the questions which are there in your school PDF, which you have shared, has those things. So we'll discuss the dipole and all the other things associated with dipoles in the next class. So that's all for the class.
Okay.
I'll share the notes. Make sure you revise these things and try out some of the questions again, whether it is from Coulomb's law or from electric field.